Now on CS50 Live today, do we look at something else that's been in the news, namely this frightening quote here. We have broken SHA-1 in practice. But what does that mean? Well, SHA-1, it turns out, is what's called a hash function, which is a special algorithm that takes input and produces output, as all algorithms do. And what it's generally designed to do is take pretty large inputs, or pretty important inputs, and reduce them to a number or a short string that represents that original input. And SHA-1, like a lot of other algorithms too, are used in any number of different contexts. For instance, SHA-1 is used in what are called digital certificates, which is a digital mechanism whereby you can prove with high probability that some document or some credit card transaction or some bank transaction or more was indeed performed by or signed by a specific person. They're also used in software updates so that when you download new software from Apple or Microsoft, you can confirm with high probability that that update indeed came from one of those players and not, for instance, from some malicious user online. Backup systems. If you're in the habit, as you should be, of backing up all of your files, your software might be using SHA-1 in order to ensure that your file's indeed correctly backed up and it wasn't corrupted, for instance, when being uploaded or copied. And it's also used by Git, the version control system with which you might be familiar on a website like GitHub. Now, it wasn't all that long ago that a well-known security researcher, Bruce Schneier, wrote this: "It's time for us all to migrate away from SHA-1." Actually, it was a long time ago. That was said in 2005, at which time it was noted that cryptographers had showed that SHA-1 is not collision-free. Specifically, that is, they developed an algorithm for finding collisions faster than brute force. Now, what does collision-free mean and what are collisions? Well, let's take a closer look now at SHA-1 itself. It's indeed an algorithm, which recall can be thought of as this black box that takes inputs and produces outputs, takes problems and produces solutions. And indeed, we generalize that black box as algorithms, but a type of algorithm is a hash function, of which SHA-1 is one. Now, a hash function generally takes as input a string or some other value and produces as output another string or a number. You can think of it more generally as the input being x and the output being f of x, a function of x, if you think back to some of your math days. Now, let's take a specific example. Suppose that we want to hash foo to some value. That is, we want to take a string like foo as input and produce as output some number that uniquely, or with high probability, uniquely represents foo, perhaps so that we can use fewer bits or fewer bytes to represent that same value. Now, quite simply, if you're familiar with hash tables, which use hash functions, we might start simply by looking at f and thinking, oh, well, this is 0, 1, 2, 3, 4, 5. This is the fifth zero-indexed letter of the alphabet, A through Z. And so you know what? We're going to represent the word foo with a hash value or integer of 5. Great. How about bar? Let's take a look at B, the first letter there. A is 0, B might be 1, and so we would represent bar's hash value as 1. And then what about a value like Baz, B-A-Z? Let's again take a look at its first character. And uh-oh, it produces the same value. So this is a collision. If you are using a hash function, like this very simple one we're using here, looking only at the first character, you get collisions if two inputs happen to produce the same output. All right, well, that's clearly my fault for having proposed such a silly, naive algorithm. Let's do something a little better with the same inputs. Foo, again, could be viewed not just as a single character, it's first, but let's look at all three. And let's convert all three of those to some integer representation, where A, again, is 0 and Z would be 25. And therefore, foo is 5, 14, 14. And you know what? Why don't we mathematically just add these together so that we're taking into account more information than just the first character. So 5 plus 14 is going to give me 33. So in this algorithm, 33 shall be my hash value. Bar, meanwhile, is going to become, of course, BAR, or 1, 0, and 17. Add those together, and we get 18, another distinct value. And Baz, and remember, this was the problem before, is going to be B, A, and Z, or 1, and 0, and 25, which, of course, is 26 when added together. So all seems to be well. Now, a hash function like SHA-1 is actually much more sophisticated than looking at a single character or adding even the number of characters together. It actually produces much larger hash values like this one here. In fact, if you were to hash, so to speak, the string CS50, you'd actually see this as output. But there's a problem with this general principle of hashing. In fact, notice what happens here. Foo, again, has a hash value of 33, but so does another word like oof. because it's the same letters. If we're adding them together so simplistically, we're still going to get 33. So that's a collision. And what that means is we can't necessarily figure out from the output what the input was, because there might be multiple inputs that produce that value. Moreover, if we're just doing addition with this algorithm, our hash values are just going to grow and grow and grow. And surely we can't count to infinity if our computers on Earth only have a finite amount of memory. So if we're hashing quux, we might get 59, or double quux 79, or triple quux, or even more than that. We might just keep counting higher and higher and higher. And we probably want to cap the number of possible hash values so we can actually store stuff in real computers in their memory. So of course, in programming, we might use something like this, the modulo or remainder operator, which recall allows us to wrap values around. And indeed, if you're familiar with hash tables, which you might think of pictorially as this is one of the ways we actually ensure that we don't run out of index beyond the boundaries of an array by making sure we wrap back around. So what is the problem then at hand? And why is this so worrisome? Well, hash functions, SHA-1 included, are supposed to be one way. Given an input, you should be able to get an output, and you should not be able to go in the other direction. You shouldn't be able to reverse engineer things so that given a hash value, you can figure out what that value was. For instance, if you saw this on the screen, you should not be able to figure out that this once upon a time was CS50 as input. Now, SHA-1 is still OK in that regard, but it's not OK when it comes to these collisions, because security researchers have originally claimed that two objects colliding accidentally is exceedingly unlikely. That is a mathematical tenet of this and many algorithms. And in fact, and don't get scared, this would be the formula with which you can compute the probability of a collision using not our simple arithmetic, but SHA-1 itself. This yields really, 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 really low probabilities that should be quite reassuring enough. In fact, the probability of a collision with this SHA-1 algorithm should be 1 divided by 2 raised to the 160th power. If we do that math, that's 1 divided by this big number here, which is 1 quindecillion. A number so big, I had to Google how to pronounce it in anticipation of saying it just now. If we actually do that math, the probability is so close to 0. You can see that 0.0000 all the way down to those digits there is the probability of a collision. Now, this seems all very abstract. How can we wrap our minds around this a little more effectively? Well, consider the planet Earth. There's a whole lot of sand on Earth. And indeed, according to NPR, there should be 7 quintillion grains of sand, give or take, on planet Earth. Now, that's a lot of grains of sand. So the probability of a collision in the SHA-1 algorithm, theoretically, would be like looking on Earth for a specific grain of sand out of all of the grains of sand on Earth. And actually, I'm oversimplifying. You wouldn't have to just check this Earth looking for a specific grain of sand. You would have to search 194 octillion planet Earths identical to this one, each of them with their own deserts of sand, in order to find that one possible collision. Suffice it to say, that should be super unlikely. And yet, computers are a lot faster than us humans. In fact, in 2015 was The Shappening, not to be confused with the hit series The Happening, starring Mark Wahlberg, at which point security researchers announced we just successfully broke the full inner layer of SHA-1. So a portion of the algorithm used for hashing was cracked using, frankly, quite a few GPUs, or graphical processing units. 64 GPU cluster was used to essentially crack the hash function in order to figure out a possible form of collision. And it's using hardware that looks a little something like this. In fact, you might have these in your PC if you're quite the gamer. GPUs are highly specialized for lots of parallel processing. So this is increasingly what CS researchers are using. They estimated ultimately, this team, that the SHA-1 collision cost today, in 2015, should be between $75,000 US and $120,000 if you rent Amazon EC2 cloud computing over a few months. And this is the key takeaway, and this is why it's so worrisome. That financial amount is within the resources of a criminal syndicate. In other words, by investing that much money in a hack or an exploit, could bad guys theoretically compromise the systems out there in the world, credit cards, passwords, and the like, that rely on SHA-1, at least in part. For more on this particular attack, take a look at this URL here. But in conclusion today, unfortunately, it was just days earlier that Shattered now followed The Shappening, wherein researchers from Google in the Netherlands announced that we have broken SHA-1 in practice. So not just a portion of the algorithm, but the algorithm itself by finding a collision and demonstrating a mechanism for generating such collisions. This research result is so significant that it even has its own logo. And ultimately, what the researchers put forth was this. This attack required over 9 quintillion SHA-1 computations. This took the equivalent processing power as 6,500 years of single CPU computations and 110 years of single GPU computations. Now, of course, they didn't use single CPUs or single GPUs. They, too, had a rack of servers and more using the so-called cloud in order to perform these calculations, which is to say that with enough money and with enough computers and CPUs and GPUs, is this attack now possible? Now, thankfully, browser manufacturers have at least been aware of this for some time. And Google, for instance, has been defending against this in recent months already by displaying a screen like this. If a website you are visiting is using encryption that uses this older version of SHA-1. In fact, if we zoom in here, you'll see that Google is complaining, a bit arcanely, of a weak signature algorithm. Now, Firefox has been planning to do this, and just days after this announcement did they further their plans to do this quickly. And Mozilla, the company behind Firefox, announced that SHA-1 on the public web is now over. And there are indeed solutions, and there have been for some time. So the real result here is humans really expediting their transition away from SHA-1. There's algorithms like SHA-256, SHA-3, and others, which not only are different algorithms, but also use many, many more bits to actually produce those hash values, so collisions are even less likely. Indeed, if I may say so myself, CS50's own website here is secure, according to Google Chrome, because we've indeed been using SHA-256 for some time. Now, for more on this, head to this URL here. And indeed, yes, this research result is so significant, it even has its own website.